Alright, so let me just give you a quick summary of what happened in the previous lecture. The previous lecture was with mixing involving noise, and we dealt with the first part of mixing involving noise, where we spoke of mixing with a sinusoid. So mixing noise with sinusoid, this is where we started, and we had Nk of t, which is the spectral component of noise associated with frequency k delta f, and we multiplied this spectral component with a deterministic sinusoid of arbitrary frequency cos 2 pi f naught of t, and we have obtained two spectral components of noise ft, of noise n of t, which are nothing but the shifted versions of nk of t to the right by f naught and to the left by f naught. So this is what we obtain, and we have realized that from equations, if you just have a look over here, that have a look at equations 8 and 9. Now from these two equations, the power spectral density of n of t corresponding to frequency k minus f naught and the power spectral density of n of t corresponding to frequency k plus f naught have some overlap with respect to their spectrums, and it is very much obvious over here. So if you just have a look, so power spectral density of k delta f minus f naught and power spectral density of k delta f plus f naught can be obtained by first dividing the power spectral density with respect to k delta f by 4 and shifting the result to the right by f naught and to the left by f naught. So the statement makes everything clear that the power spectral density associated with equation 8 and 9 have some common spectral range, or there is an overlap between spectral ranges of these two respective spectral densities, and we have arrived at a conclusion saying that the power spectral density corresponding to the superposition of both the random processes or the spectral components, okay, we'll have a look at equation 15. The power spectral density corresponding to nk minus f naught of t and nk plus f naught of t is equal to power spectral densities of their, or sum of the power spectral densities of their individual terms, or the overall PSD is equal to sum of individual PSDs. That is what we have seen. So from equation 15 I can simply say that superposition of power applies when you are trying to superpose two random processes which have some common power spectral density or some common spectral ranges between them. Alright, now we went ahead and we tried to superpose two random processes which are basically spectral components of random process n of t. Now if you have a look over here, so just have a look. Alright, now have a look at equation 25 and 26. So we tried to superimpose nk minus f naught of t and nl minus f naught of t, which are spectral components of n of t, and we have realized that the power spectral density with respect to equation 25 and 26 have a complete overlap of their spectrum, and still we have proved that the power spectral density of the combination between both of them is equal to the power or the sum of the individual powers or sum of individual power spectral densities. This is what we have. So I can simply summarize by saying that, have a look over here, I can simply summarize by saying that when you are trying to superpose two spectral components of noise and if there is a overlap between their spectrums, either partially or in entirety, superposition of powers apply. And that is what we have seen. Alright, now let us have a look at the second part of this particular concept of mixing involving noise. And the second part basically talks about mixing noise with noise. So let me just write it down properly. Noise mixing noise. So this is the second part. So let us just go ahead. Now consider the spectral components of n of t corresponding to frequencies corresponding to frequencies k delta f and L delta f. Okay, they are n k of t is simply equal to ck cos 2 pi k delta ft plus theta k. And on a similar note, I have n L of t, which is equal to CL cos 2 pi k delta ft plus theta L. So we are just going for the compact trigonometric Fourier series representation, nothing apart from that. Whereas in the previous lecture, we dealt with the actual trigonometric series representation. So let me call this as equation 27 and let me call this as equation 28. Now let us mention what CKCL and theta k theta L are. CK comma CL are Rayleigh random variables, and theta k comma theta L are uniform random variables. This is already known. And besides this, CK, CL and theta k theta L are independent to each other. This is what we have. Now mix, one second. Alright, so let us get into the actual part. Mixing nk of t with nl of t, we get, so let's have a look, nk of t times nl of t. This is nothing but ck cos 2 pi k delta f plus theta k. Now this is getting multiplied with CL cos 2 pi L delta F plus theta L. So this is what we have. Now we can simply go for the formula twice of cos A cos B. Okay, so let me just also mention something over here for more clarity. We get from equation 27 and 28. Okay, now if we go for twice of cos A cos B formula, we are going to get something like this: half of CKCL cos, we have, let me just write it down, cos 2 pi k minus L delta f t plus theta k minus theta L plus half CKCL cos 2 pi k plus L plus, times delta ft plus theta, theta k plus theta L. So this is what we get, and I'm sure the result is very obvious to you. Now let us further analyze the situation over here. Just a second. Alright, now let me just call this as equation 9. Beg your pardon, this is not equation 9, this is equation 29. Okay. Now let's go ahead. Let n k minus L of t be equal to half CKCL cos 2 pi k minus L delta ft plus theta k minus theta L. Let me call this as equation 30, and n k plus L is equal to half CKCL cos 2 pi k plus L times delta ft plus theta k plus theta L. So this is equation 31. Now, okay, I can say one thing. One second. Okay, from principle of minimum astonishment, it can be said that theta k minus theta L and theta k plus theta L both are uniform random variables. So this is what we have. Now let us proceed applying statistical average to equation 30. 1 second. To equation 30 we get expectation of n k minus L of t, which is equal to expectation of, let me get half, ck cl cos 2 pi k minus L delta f t plus theta k minus theta L. This is what we have. Let me just correct this. Okay. Now we already know that each of the random variables are independent to one another. So I can simply write this equation as half of ck bar times cl bar into expectation of cos 2 pi k minus L delta ft plus theta k minus theta L. Okay, but as theta k minus theta is a uniformly distributed random variable over the interval minus pi to plus pi, we have expectation of cos 2 pi k minus L delta ft plus theta k minus theta L equal to 0. So expectation of n k minus L of t is equal to 0. On similar lines, I can also say that expectation of n k plus L of t is also equal to 0. So let these be equations 32 and 33. So this is what we have. So I can simply say that expectation of nk minus L of t plus nk plus L of t is equal to expectation of n k minus L of t plus nk plus L of t, which is equal to 0 plus 0 is equal to 0. So let this be equation 34. Now let us see, for superposition of power, consider nk minus L of t plus nk plus L of t. for superposition, of power to apply, we know what the situation is. Limit t tends to infinity, or integral 1 by t integral over t, expectation of n k minus L of t times n k plus L of t should be equal to 0. So let me call this equation 35. So what do we have? Let's have a look over here. Let me just first of all correct this. Okay. Now, okay. So consider from equations, what do we have? From equations, let us go for the equations. From equations 30 and 31, we have nk minus L of t into nk plus L of t. Okay, we'll take the expectation later. I can simply write it like this. Just a second. Okay. 1 second. Okay. Now let me just take you there. Alright. Now multiply. If you multiply equation 30 and 31, we'll have 1/4 of ck square cl square cos of two terms, or cos of some angle and cos of another angle. So if you simply multiply, you're going to get something like this. Let me just write down 1/4 of ck square cl square and cos 2 pi k minus L delta ft plus theta k minus theta L into cos of 2 pi k plus L delta ft plus theta k plus theta L. So this is what we have. This is equal to, by going for the formula of twice cos AB, I can simply write this as 1/8 of ck square cl square cos 2 pi L delta f t plus 2 theta L. This is what we have. Just a second. Okay. So twice of cos AB, which is equal to cos A plus B and cos A minus B. So I'll simply write it like this, and I have plus cos 2 pi k delta f t plus 2 theta k. So this is what I get. Alright, now let me just go further ahead and call this as equation 36. Alright, now applying statistical average for equation 36, we are going to get this. The LHS is going to be expectation of nk minus L of t into nk plus L of t, and this is going to be equal to 1/8 of expectation of ck square into expectation of cl square into expectation of, we have cos 2 pi L delta ft plus 2 theta L plus expectation of cos 2 pi k delta ft plus twice of theta k. So this is what we are going to get, and this is all possible because of the independent nature of the random variables involved, and we know that the expectation of the cost term and the expectations of both the cost terms is equal to 0, as theta k and theta L are uniformly distributed. I have something like this: 1/8 of ck square bar to cl square bar times 0 plus 0, which is going to be equal to 0. So one thing is obvious: the expectation of the product is independent of time. Yes, of course it is 0, but it is independent to time. So let me just write down over here equation 37. Alright, so the statistical average of nk minus L of t into nk plus L of t is independent of time, or in other words, there is no point in now going for the time average of this equation 37. So I can simply say that equation 35 holds good in this case. So equation 35 holds good, and the superposition of nk minus L of t with nk plus L of t has superposition of power applicable. Alright, so I can simply say that power of nk minus L of t plus nk plus L of t is equal to power of nk minus L of t plus power n k plus L of t. So this is what we have, and we very well know that the spectral component of noise located at frequency k minus L, if you just have a look over here. Alright, look at equation 30 and 31. Now, we very well know that the power, since equation 30 and 31 represent two stationary random processes, the power associated is simply the expectation of equations 30 and 31, and it is nothing but the square of the average of these. Similarly, the square of the statistical average of these. So let me just write down over here. So this is simply equal to Ck square Cl square by 2 square whole bar by 2 plus, again I have Ck square Cl square whole bar by 2 square by 2. So this is what I'm going to get over here, or in other words, it is the sum of same components. So I can simply write this one as Ck square Cl square whole bar divided by 4. But since Ck and Cl are independent to each other, I can write this as Ck square bar to Cl square bar whole divided by 4. So it's very much obvious that since superposition of power applies, superposition with respect to PSD should also apply, or in other words, power spectral density of the sum is equal to power spectral density of nk minus L of t plus n k plus L of t. 1 second. So this is nothing but plus power spectral density of n k plus L of t. So we arrived at a similar conclusion over here also, which is nothing but, let me just take you back a bit, or let me just write it over here itself. But okay, I have over here, but PSD of nk minus L of t plus nk plus L of t is simply equal to PSD of nk of t into n L of t. So it can be said PSD of Nk of t into NL of t is simply equal to PSD of Nk minus L of t plus PSD of Nk plus L of t. So this is again a similar conclusion that we obtained with respect to mixing noise with a sinusoid. So let me just give you a quick summary over here. Now what have we done exactly? We have taken two noise spectral components and we have mixed both of them, and the mixture has given rise to two spectral components, one located at frequency twice of p k minus L delta ft. So let me just represent it over here. This entire thing is a spectral component located at frequency k minus L delta f, and this entire thing is another spectral component located at frequency k plus delta f. So mixing noise with noise also generates a new spectral components of noise, which are again the shifted versions of the spectral components that we have originally mixed. And we came to the realization that even in this case the superposition of power applies, and automatically the superposition with respect to power spectral density also applies. Alright, so this is what we have, and you very well know what power spectral density of this is. Simply nothing but Gn of k minus L delta f, and this is nothing but Gn of k plus L delta f. So this is what we have. Alright, so when you mix either noise with a sinusoid or when you mix noise with noise, the superposition of power applies in both the cases, finally giving us a power spectral density of the overall thing as the sum of the power spectral density of the shifted noise spectral components. So this is a summary of this concept of mixing involving noise, and we'll observe in the later lectures how important this result is.